Hello everyone, I'm Mariam Najafi, a PhD student from the University of Technology of Troyes in France. I work in the Computer Science and Digital Society Laboratory. This article is co-authored with Lies Houchy and Marc Lemercier. We published an article entitled Decentralized Reputation Model based on Bayes' theorem in Vehicular Networks at the IEEE International Conference on Communications. This presentation contains 5 sections, including introduction, related work, proposed reputation model, and validation, finally, conclusion and future work. A vehicular ad hoc network is a promising research venue offering many useful applications and services. Vanet provides communications between vehicles as well as between vehicles and stationary equipment. The primary purpose of inter-vehicle networks is to provide safety and comfort for drivers and passengers. Vanet's technology would help prevent accidents, improving the traffic control system, and make driving safer and more comfortable. To be deployed, such technology does not need any centralized data processing organization. Thus, vehicular networks can be easily extended. As illustrated in this figure, a vehicular network composed of a set of onboard units, OBUs, deployed on vehicles and roadside units positioned along the road. Vehicular network includes two communication modes: vehicle to vehicle network V2V, as shown in this slide, and vehicle to infrastructure network V2E. In this slide, we can see the global architecture of vehicular ad hoc network. However, in Venice, vehicular applications and services are always deployed in unattended and even hostile wireless environments, where vehicular nodes are easily captured and attacked. Therefore, Venice are vulnerable to many types of threats. The modified messages or dropped messages by attackers may include induce the traffic authority center to make wrong actions, which leads to traffic disorder and road accidents. In practice, a vehicle node should check the validity of any received message before making decision to forward or drop the received data. Few trust models have been studied for Vanet. Various trust models have been developed for dynamic networks. There have been many studies related to security protocol for behavioral analysis. However, some of these works are limited by the simplified threats hypothesis assumed in the vehicular environment. The unique characteristic of the vehicular network make it difficult to use these trust models directly. Some existing trust works don't sufficiently deal with the following issues: a non-cooperative behavior of non-forwarding packets, and two, a generation of fake messages for the unintentional reason. Therefore, a robust trust approach should consider various behavioral conditions and uncertain situations. In this slide, the organigram of our work is presented as follows: watchdog method, Bayesian statistical filter, quantitative score, classification, and validation. We propose a robust decentralized reputation model based on Bayes' theorem to filter out malicious vehicles in vehicular networks and calculate the probability of malicious behavior. The architecture of the proposed model is shown in this figure. In order to calculate the quantitative score, each node receives the neighbor's opinions based on the monitoring fast watchdog method. Also, it uses the Bayesian statistical filter to estimate quantitative score. Our model designs a score to each node to determine its state. Each vehicle takes one of the following states: malicious MA, heavily suspicious HS, lightly suspicious LS, and normal NO. Three thresholds separate the ranges H1, H2, and H3. In watchdog method, each vehicle inspects its neighbors by overhearing their transmissions and give them a score. Once a quantitative score has been allocated, it decides whether to interact with the vehicle or not. The watchdog mechanism has proved its efficiency in several areas, particularly for monitoring nodes' behavior within dynamic networks. In watchdog, the node sending a packet then monitors the adjacent node's behavior and can gain knowledge on how that node behaves. For example, C1 drops the packet off or transfer it. If CO wants to send a packet to C2, firstly, it has to send its packet to C1. Then CO overhears whether C1 has sent the packet to C2 or not. We study the concept of classification and introduce the concept of misclassification cost, which is called beta. Each time a misclassification occurs, we calculate the transition cost between states. The cost values are introduced in this table, considering various anomaly situations. For example, C equal O, correct classification, a node stays in the same state. For example, NO to NO. C equal 1, incorrect classification of type 1, the transition of one hop range, for example, NO to LS. C equal beta, incorrect classification of type 2, the transition to two hop ranges, for example, NO to HS. C equal 2 beta, incorrect classification of type 3, the transition to three hop ranges, for example, normal to MA or MA to NO. 2 beta time more costly than 1. To evaluate or propose model's performance, we conducted extensive simulation using MATLAB under different network configurations. In our simulation, we varied the proportion of malicious node taken into considering four different scenarios. Scenario 1, 5%. Scenario 2, 10%. Scenario 3, 15%. And scenario 4, 20%, which are depicted in this slide. Also, for each of these scenarios, we consider our network composed of 20, 40, 60, 80, and 100 vehicles. Then we varied the value of the misclassification cost. 0.25, 0.50, 0.75, and 1. The purpose of these simulations scenarios is to find out the best setting for our model. In figure A, we consider 5% of the nodes as malicious. It can be observed that there is a decreasing TCR trend with the increasing number of nodes. The TCR values are always greater than 2. However, when the number of vehicles exceeds 60, we have a similar and constant TCR value for all cost cases. We note that TCR remains almost between 2 and 3. This is an interesting result, which confirms that our filter is accurate and precise. The best value is achieved by cost 0.5. In figure B, we show the second scenario results, where we consider 10% of the nodes as malicious. In this scenario, the cost value of 0.5 has the best result of our model. We observe that when the number of nodes reaches 60, a sudden change has occurred in the TCR value. There is not much difference in the value of TCR for the range of 80 to 100 nodes. As in the previous scenario, we observe that TCR is still greater than 1, which proves our filter precision. In the third scenario, illustrated in figure 3. We increase the number of malicious nodes to 15%. We observed that when the number of vehicles is between 40 and 100, the curves show the values between 1.05 and 1.35 for TCR. When the number of vehicles is below 80, the cost equal 1 is more interesting. In the last scenario, illustrated in figure D, we consider that 20% of the nodes are malicious. In these scenarios, the cost value 0.25 shown in green is more significant, as the graph line is substantially higher than the rest. As illustrated in figure D, when the number of nodes increases to 100, we note that the TCR values are decreased. The TCR values are still considered acceptable because they are always superior to 1, which still indicates the precision as well as the accuracy of our proposed filter. Based on these TCR results, we can conclude that our filter offers great precision, even with a high rate of maliciousness. We observed that Vanet is prone to critical race threats and attacks due to its unique characteristic and its dynamic topology. So, we proposed an accurate decentralized reputation model that calculates the behavior score and evaluate the reliability of nodes in vehicular network. We formulate the problem using the Bayesian filter. Then we describe our classification strategy and compute the precision and accuracy of the proposed filter. The model monitors the behavior of vehicles where each node can decide to interact with its neighbors. By analyzing their behaviors, we conduct extensive simulation to illustrate the validity of the proposed reputation model. The results have shown an interesting rate of detection regarding the precision and TCR value under various network conditions. In the future work, we plan to present a prediction function within the proposed reputation model. We will integrate a Markov process to predict each node's behavior in the vehicular network. Finally, we would like to thank FEDER, Region Grandes, and the MSER for the financial support of this research. Thank you.